And we start off and we talk about, this is really nice, okay. A fluid, okay. The definition, first of all, of a fluid. The official definition in chapter 1. Put that down. It's a substance that deforms continuously when acted upon by a shearing stress of any magnitude. How many people have had Me218 strength materials? Okay, almost everybody, of course. Take a piece of copper plate. Copper plate. And apply a force F on it. Here's the plate. I don't know, an inch thick, 6 by 4, something like that. Apply 400 pounds on it. The top of it. This is fixed at the base. When you apply that force to it, you know, from Me218, for instance, there's the plate. Now, again, here's the ground. Now I take a layer of water. I apply a force on it. No, doesn't look like that when I'm done applying a force to that plate on top of water. Think what would happen if you applied a force to that plate on top of a water layer. I applied 10 pounds. Would the plate ever stop? Of course not. You applied 10 pounds. This is room's flooded with water this high. I'm walking in the water with my knees. I put a styrofoam plate on top of it. I push on with 2 pounds. 2 pounds with my finger. Is it going to stop me from pushing ever? No. And the key word is, it's continuously. This will deform a little bit, then it's going to stop. But a fluid will deform continuously. So yeah, that's a fluid. Air, 10-weight oil, JP4 jet fuel. You name it, these things we live with, water. They're fluids. Now there's different kinds of fluids though. We're all used to fluid water. Coffee. Working there to there. Works really nice. Works really nice. What's in this cup? Went in that cup. Now, fill that cup there with cold air. Try and pour that cold air in that cup over there. Oh, it won't do it. It won't do it. It'll spread out when it comes out, and it'll go all apart in a big plume. Why? Because the molecules are not attached to each other as strongly as they are in that liquid. Are they both fluids? Oh, sure. Of course they are. Put air in here. Push on a plate in air. It was told. Yeah, they're both They're both fluids. Liquids and gases, but not solids. Not solids. Well, maybe not quite. Maybe not quite. Take the cap off the toothpaste. Turn it upside down. Does it run out? Really, no. This has been in the car for 2 hours at perfect temperatures. No. What makes it come out? I've got to press on the tube. Okay, so it takes an initial stress, shearing stress, to move it, to get it moving. Once it's moving, it moves pretty good. But it takes that initial shearing stress. It could be, you know, some very thick things like some epoxies, you know, you can come check down, they won't come out until you squeeze a tube with a plunger. So yeah, those things are kind of like fluids, but we won't discuss those in this class. We're not going to worry about, you know, toothpaste and epoxy and things. We'll worry about water, air, oils, things like that. Helium, freon, you name it. So that's a big difference in that. And we're also going to look at 2 sets of units. You know, a lot of textbooks now, they are almost all in SI, which is so much easier than the British system. So much easier. But unfortunately, the real world doesn't go that way yet. So our textbook, I forget the percentage, but it has quite a few, I'll call it English, British gravitational. Quite a few problems, whether they're example problems or homework in English, and then a lot of SI, but you graduating have to be conversant in 2 languages, otherwise you're not going to show off very well in the real world. You have to know 2 languages, forward and backwards, really, really well. The easy one is SI. The hard one is English engineering. For instance, how many centimeters in a meter? Well, I guess okay. How many millimeters in a meter? I'll tell you, about 1,000. How many cubic centimeters in a liter? I'll tell you, it's 1,000. Do you get the point? Everything in SI. Would you go out there and close that door, please? Oh, okay, thanks. Everything, every conversion factor. Okay, let me tell you another one. 1 joule divided by 1 second. What is it? Joule per second. Yeah, 1. Is it 1? Yeah, it's 1. Okay, 1. Everything conversion in SI starts with a 1 times 10 to a power. You can't get any easier than that. Now, you tell me this. How many pints in a quart? How many quarts in a gallon? How many gallons in a barrel? Nothing starts with 1. Nothing. Want to memorize that stuff? No. You don't memorize this right here. You know. Memorize that stuff. But it's still kind of embarrassing. You think, well, I don't know, but I've got this thing in my pocket. Yeah, I'll tell you in a minute, okay? You know, gee, that's okay, but I mean, 55 gallons in a barrel, you know, blah, blah, blah. No, it's awful. It's awful. Power. How many foot-pounds per second on a horsepower? Well, you know, how many watts in a kilowatt? Well, I'll tell you. How about 1,000? 1 times 10 to the third. So, yeah. I mean, don't you wish the whole world was SI? Of course we all do, but it's not. And you live in a country you live in the worst country for it. The country that still has both unit systems. So you have to be really, really, really good in both of them. That's why my point is. That's why when we select a textbook, we make sure the textbook has, if we can find it, dual unit systems in it. Because we know the more you practice, the better you get. The problem is most people work problems in SI where they need to practice in English engineering. Okay, well that's neither here nor there. There's problems here. There'll be problems on homework of both. There'll be problems on tests of both. You can use your smartphone for conversions. There's conversions in the inside back cover too, SI to British gravitational. So your choice, but there will be both kind of problems for homework and exams. Okay, let's just briefly go over the two unit systems. Let's do SI first. Okay, force is in newtons. Our mass is in kilograms. And of course, length is in meters. Okay, let's do British gravitational. Force is in pounds. Mass is in slugs. Length is in feet. And they both have seconds for time. There's a third unit system that has force in pounds force, mass in pounds mass. But this is the British gravitational. You don't put a subscript on this guy because you know if it's in this system and it says pounds, it's got to be force. So you can skip putting the subscript F on pounds. Unfortunately, you don't deal with pounds under mass, you deal with slugs. These are not little creepy, crawly, slimy things on the floor, okay? These aren't snails and slugs. A slug is a unit of mass. How big is it? Anybody know how many pounds mass are in a slug? What's the gravitational acceleration in English is? 32.2, right? There you go. 32.2 pounds mass in one slug. That means a slug is more massive than a pound mass. A slug is more massive. Okay, so those are the two unit systems. When you work problems for homework or exams, that's what you use there. Okay, now let's take a look at, let's see, pressure. Let's look at some other things here. Oh yeah, okay, here it is right here. Okay. If you've had physics and or thermal, rho, density, mass per volume. If it's in SI, kilograms per cubic meter. If it's in British gravitational, mass, slugs per cubic foot. Specific weight, gamma. Weight per volume. SI, weight, weights of force. Newtons per cubic meter. British gravitational, force, pounds per cubic foot. Specific gravity. Okay, gamma of the fluid in question under gamma of water at a certain temperature, like I think it's 4 degrees, you have 4 degrees C. Or it's 39 degrees F. So it's a ratio. A ratio is dimensionless. So it's a dimensionless number, specific gravity. Gamma is the specific weight of the fluid you're studying, divided by gamma of water at a certain temperature. An ideal gas, or perfect gas law, P over rho equal R times T. P and T are absolute values. Absolute pressure, absolute temperature. We'll mention absolute pressure in just a little bit. You know absolute temperature at 273 degrees C to get degrees K. Add 460 degrees F to get degrees R. It's in the book. This is for gases. So the good news is, what we're studying in this class, pretty much all the gases behave like that. As long as you're around ambient conditions, air, hydrogen, oxygen, hydrogen, behave like that. Viscosity. Viscosity is mu. Viscosity is mu, sometimes called absolute viscosity. All these properties are in the back of the book, page after page after page of properties, the graphs of them, physical properties of fluid. Appendix B. I'm giving you, on both exams and the final, copies of these out of the back of the book. You'll get a package of properties, probably 8 or 9 pages long. You'll have these same properties on the exam, so learn how to read them. That's the key point. I'll pick them up after exam 1. Your name's on, I'll keep them. Before exam 2, I'll pass them out. You use them for the test, pass them back to me, I'll keep them. The final exam, I'll pass them out to you. You use them, pass them back to you when you're done. So they'll be your package. You can mark them up with a pen, pencil, whatever you want to do. Mark them up, you get it back for each exam, including the final. Okay, now, let's get back to our definition of mu. Mu, this is the big property that's different in a thermal aspect.
What page was that on?
We'll look afterwards. I'm not going to, this is shearing stress. Tau is shearing stress from inlet weight. Now, du dy, this is called a velocity gradient. So if we take a simple case, again, take that plate on water, and here's water. Maybe the velocity looks like this. This would be capital V velocity, and then this is typical of how the velocity might look between the plate. Let's make it linear to make life easy right now. We don't get too exotic, day 1. So this is called a linear velocity gradient, because it's a straight line. Velocity versus the height. The height is y. The velocity is lowercase u. U is a function of y. Differentiate that, that's called the velocity gradient. You take the velocity gradient, like in a bearing, one surface is rotating, one is stationary, moving. You've got 10 weight oil, that's mu, multiply, where do you get mu oil? Back in the book, in the appendix, what's the temperature? I don't know, 120 degrees Fahrenheit. Go back to the book, find mu, put it in here, multiply it by du dy, which is v divided by the separation distance. And that's going to give you the shearing stress that the fluid creates. Okay. So viscosity is a property which is useful to determine shearing stresses. Okay. And then there's another property which is nu, Greek letter nu, which is mu over rho. This is called kinematic viscosity. So there are 2 possible viscosities. One is a real thing. The real thing is this one up here. This is really the viscosity. If someone just says viscosity to you, then you assume they mean this one. But that's why they're also called absolute and kinematic, just to be certain that someone knows what you're giving them. If you say viscosity, though, the default definition is here. Kinematic viscosity is this value divided by the density rho. This thing comes in handy, we'll see later on in some equations. It appears, the ratio mu divided by rho appears in some equations. So it's given a special name called the kinematic viscosity. Okay, the units, the units. Okay, if you don't memorize those things, and I hate to, if you don't memorize them, then figure out what they are. What is this guy? Force divided by area. Okay, so force divided by area. The area, let's just say length squared. What's this guy? Velocity, length over time. What's this guy? Length. Okay, cancel, cancel. So figure it out that mu is F. This guy's in the denominator. This guy's in the denominator. Put him up here. Ft over L squared. If it's new kinematic viscosity, divide that guy by mass divided by length cubed. Density, mass divided by length cubed. We go back here. Viscosity, English units, what are they? Pounds second per foot squared. Look at it. Pound, over there. Pound second per foot squared. Yeah. I don't memorize that stuff. I derive when I have to. So there's no reason to memorize it because you know you can derive it. Where does it come from? The basic governing equation. Right there. Okay. Now let's go on to our last two properties. The next one. By the way, before we forget it, let's just go ahead and put this graph up here. This is shearing stress tau there. This is dy, velocity gradient, sometimes called the rate of shearing strain, but the velocity gradient is sufficient. If this is air, this is water, this is oil. Oh yeah, we know, intuitively, we know oil is very viscous. It'll give you very high shear stress for a certain value of du dy. Given a value of du dy, air is not very viscous. Water's in the middle of the road. Oils are very viscous. Notice they're linear too, which is very important. They're linear. Those fluids are called Newtonian. There are many which are not linear, which we won't study in ME 311. Examples. Toothpaste. No, it's not Newtonian. Latex paint. No, it's not. When you put that paint on a brush, put that brush in water, pull it out of there, oh, the water just runs off. You'd be running for the wall to get up on the wall before it ran off your paintbrush. No. You put that in there in latex paint, take it out of there, kind of turn the brush. It stays on the brush fibers until you get to the wall, then you either roll it on or you paint it on. Yeah, it's different. It's not linear. It's not linear. The graphs are in the book, by the way. Quicksand. No, not linear. No, quicksand. The more you try and get out, the harder it is for you. You got to move really, really slowly. Don't try and put your foot out because you're going deeper. It's all, this graph tells the whole story. I'll just show you a couple. Some go like this, some go like that. Here's quicksand, here's latex paint. There's toothpaste. And they do stuff like that. But that's just for your own sidelight right now. What you're worried about are the three things us MEs and CEs look at most in life. Aeros and MEs, aeros and CEs, mostly MEs, engines and things like that, you know. So we're not going to worry about those other exotic ones. We're going to worry about things like these three right here. They're all going to be Newtonian fluids in ME 311. Okay, let's go to one more. Let's see, here we go. Surface tension. Before I forget, of course, we're being videotaped by our friend here, Matt. Matt, you're an ME student, right? What year are you in?
A lot.
Did you start here? You started?
Yeah, I started here.
Oh, did you? Okay, okay. But you're taking senior classes now, right?
Yes.
Okay, good for you. Okay, so it's close.
Yeah, very close. It should be my last quarter.
Okay, good. So he'll be at every class meeting, videotaping the lectures here. Okay, surface tension. The symbol for that is sigma. Sigma. And sigma is the force per unit length. So sigma has dimensions of force per length. Okay. Here's a reservoir. I put this tube in there, invert it. The liquid will rise up in that reservoir, something like this. You might have seen a mercury barometer on the wall, and the mercury rises up that glass tube and you read off what the mercury level is. The guy at night in the news says, okay, the weather forecast, cold front's coming down from Canada, and the barometer's dropping. It's right now 30.05 inches of mercury. You say, what do you mean there's mercury dropping out of the sky on people's heads? No, no. Now, ask any of your friends at night, say to them, what does he mean when he says the pressure is 30 inches of mercury? Most folks don't have the slightest, of course. They don't ask them their tire pressure. Look, they'll tell you 32 pounds in my tires. Do they really mean 32 pounds of air in your tire? No, they're taking shortcuts. They mean to say 32 psi in my tire. Well, if you put mercury in here, fill the tube with mercury, invert it, thumb off there, the mercury rises up. At this point right here, mercury does this. Around the glass perimeter, where the glass and mercury are in contact, the mercury is being pulled down. That's surface tension. That's surface tension. Take water. Here's a tube of water. Do the same thing. Doesn't work quite as well. But looks like that. The water is being pulled up by the glass, it seems like. So it's a property. It's a property of the fluid and the temperature. So that's why it's force per unit length. What length is this length? It's the perimeter of the glass tube, the perimeter, pi times d. So that's a phenomenon that occurs quite often that in fluids that you should be aware of. What's this thing called surface tension? Try and put, you can do it if you do it real carefully, a dime on water. If you're really, really, really careful, you can float it on water. It won't sink. It won't sink. Something's pulling it up around the perimeter. Something's pulling it up. That's the water doing that, and that's the surface tension in the water. So those are all part of the concept of surface tension. Okay, I think that pretty much covers all of our important properties in there. So let's take a look then at pressure. All right. Now, let's go back over here, leave this thing on here. Let's talk about pressure. It's one of the big concepts in our first fluids course. What do you call pressure in any 218 string? What's pressure? What's stress? Force per unit area. What's pressure? Force per unit area. Right. Different, but just different. Those guys are solids. These guys are liquids. Okay, let's start off by absolute pressure. We'll put them all down. Gauge pressure. Okay, absolute. Reference to zero pressure. Referenced to local atmospheric pressure. We'll use our standard pressure, 14.7 psi. And I think for our we'll just use 101 kPa. It's like 101.3 something. 101 kPa. So these are the standard pressure values. We're not going to use the value in Pomona, which is, I don't know, 800 feet above sea level. These guys are at sea level and, I don't know, 34 degrees latitude, something like that. They're standard values. We'll use those. Okay, gauge pressure. Reference to local atmospheric pressure. The word local means where you are when you make the measurement. Local means where you are when you make the measurement. If you're in Pomona, at Cal Poly Pomona, it's the pressure here. That's the local atmospheric pressure. If you're in Denver, Colorado, it's the pressure in Denver, Colorado at that time of day, that day of the year. So that's reference to where you are. Okay. Now, let's talk about these guys. Gauge pressure can be positive or negative. These guys are always positive because they're reference to zero. No such thing as a negative absolute pressure. Negative gauge pressures are sometimes called vacuum pressures. So you hear the word vacuum pressure, and some gauges will show you positive pressures and vacuum pressures. That's what they mean by that. Okay. So let's draw a little picture here that shows these pressures. The pressures, I'll put on the board the values of some conversion factors too for you. Let's start off with zero pressure down here. Zero absolute. And let's say that this is the local atmospheric pressure. And let's call that 101 kPa. And let's call the pressure up here PA. If I measure PA from the local atmospheric pressure, reference to local atmospheric pressure, that's this line right here. And PA is going to be, this is given, 200 kPa gauge. This is 101 kPa absolute. This pressure is 101 plus 200, it's on a scale. 301. If the pressure is down here, and let's say that it's minus 50 kPa gauge vacuum, then the absolute pressure always is measured from the bottom down up to here. 101 minus 50, 51. 51 kPa, and that's absolute. Now, in the textbook, I think he gives us a big hint. Let's see what pressures are here. This picture is in the book too, by the way. Yeah, so on page 50. Okay. Here's what he says in italics. In this textbook, pressures will be assumed to be gauge pressures unless they're specifically designated as absolute. In this book, for homework, in an exam, for a problem, the pressures are assumed to be gauge unless it specifically says absolute. So if I give you a problem on an exam and it says the pressure is 50 kPa, that means you assume that's gauge. Unless I put that, then it's absolute. So that's the default rule. The default rule is pressures that just are in kPa, assume that they're gauge. Unless they're absolute, there'll be a paren ABS after it. Or the problem will say the absolute pressure is 50 kPa. Okay. In English engineering or gravitational, British gravitational, if someone tells you pressure of the air in your tire, make it easy, is 30 psi. Okay. How do they measure? Oh, probably a tire pressure gauge, I would suspect, a tire pressure gauge. How does a tire pressure gauge work? Oh, a typical example. There's a spring in this thing, and in the stem pops up, and you read it. Or there's a circular gauge you put on your tire, and you read it. Take the spring away one. What's the pressure in your tire doing to that thing? Oh, it's compressing the spring as it pushes it up. What's it working against? What's outside that pencil-like device? Atmospheric pressure. So what's it measuring the pressure with respect to? 30 psi means that's 30 psi gauge. And we don't say, nobody says 30 psi gauge. We say my tire pressure 30 psig. That's standard practice. Psig means gauge. If somebody says, well then what's the absolute pressure of the air in my tires? There it goes. There it is. You're up here now at 30 above low atmosphere. 30. Local atmosphere, I think I erased it. Yeah, there it is. 14.7. 30 plus 14.7. 44.7 PSIA means absolute. That's just the way most engineers work. They use PSIG for gauge pressure, PSIA for absolute pressure. But in the world of SI, you don't say this. There's no such thing as a K-pag. There's no K-pag in the world. So what do? You have a rule. Textbook rule says, if I don't put anything after KPA, you assume that it's a gauge. If it's absolute, I'll put ABS after it. Just so on the exam, people say, Professor Biddle, what do you mean by that KPA? I'll say, go back to the default rule, what it said. You don't want to get confused on an exam, a timed exam. It makes life miserable. Okay, so that's the pressures now. And the guy that says, what do you want your tires at, 35 pounds? Say, no, I want 35 PSI. Because they take a shortcut. They just say pounds. They really mean PSI, of course. They say pounds. Okay, now let's take a look at some problems similar to homework. Let's see which one I look at here. I'll take this one first because this is 177. 177. This book, by the way, why did we use this textbook? It is the most popular fluid mechanics textbook in the United States. It's the most popular fluids textbook in the United States. Okay, that's why, and there's a reason why. It's very well written. Very well written. Okay. 177. Yeah, there it is. You have 178 and 180. They're all the same kind of problem. They're viscosity problems. Viscosity problems. So we don't need this. Okay, I'll read it for you. It's a snow sled. The sled shown in the picture slides along a thin horizontal layer of water between the ice and the runners. So here's the sled.
Problem 177.
Here's ice. I'm going to expand it up. Here's water. Here's the runner of the sled. The blade, that's the skate blade. The horizontal force that the water puts on the runners is equal to 1.2 pounds.
Here's the, okay, I'll put this for the ice.
The sled's speed is 50 feet per second. The sled, the runner, the blade, runs on water, not ice, water. The total area of both the runners in contact with the water is 0.08 square feet. The viscosity of water, if they didn't give it to you, it's in the back, but they gave it to you. Viscosity of water, 3.5, so this is mu. They didn't say kinematic, they just said viscosity, assume it's absolute, 3.5 times 10 to the minus 5. pounds seconds per foot squared. Determine the thickness of the water layer under the run. D. Find D. Keep reading. Assume a linear velocity distribution in the water layer. Assume a linear velocity distribution in the water layer. So draw this. V is the velocity at the top of the water layer. It goes down to 0 at the ice. The velocity at a solid surface is assumed to be at rest in the water. It's called the no-slip condition. Right here, this is called no-slip. It means the water doesn't slip along the ice. The velocity of the water at the surface of the ice is assumed to be 0. We'll make that assumption pretty much throughout this whole course, the no-slip condition. Okay, so I erased our equation. So we have our tau equal mu du dy. Okay, our shear stress we know is force over area. Mu du dy. We're measuring y from here up like this. Okay, force is 50 pounds force. 50 pounds. Oh, 1.2 pounds. Velocity is 50. Which reminds me, if I put something on the board which doesn't make any sense to you, or it looks like I made a mistake, let me know right away. I don't want to have to copy the mistake on the paper and come back next class meeting and change it. So I don't mind. I've got to correct it right away. And you know, I'm not perfect. I make mistakes. So just let me know, and we'll change it on the board right away if something's wrong. Okay, 1.2 divided by area, 0.08. Equal mu. Okay, there's mu right there. 3.5, 10 to the minus 5. Pounds second per foot squared. Multiplied by du dy. Don't forget, it's a linear profile. So, you know, lucky you. Du dy, if it's linear, equals delta u over delta y. Delta u at the top, v. At the bottom, 0. Delta y at the top, d. At the bottom, 0. There it is. Du dy is delta u over delta y equal v over d. V, 50. D is going to be in feet. Check it out. Better come out right here. Okay, seconds divided by seconds. Feet squared here, feet gone. The right-hand side, pounds per foot squared. Left-hand side, pounds per foot squared. Good, we're good to go. Solve for D. It'll be in feet. 7.7, 10 to the minus 4. One 10,000th of an inch. 1/10,000th of an inch. That's the amount of liquid water between the blade surface and the ice on the King's hockey field. Not a lot. It doesn't take a lot. It doesn't take a lot. but there is a layer of water under there. Okay, I did that just to kind of show it. Matt, did you give me a signal? I'm sorry about that.
No, I got it.
Okay, thanks. I want to show you how you set the homework problems, and I'll go over it again when you pass your first homework statement. But do that. The first thing you do is you draw a sketch if it's appropriate. I mean, we're engineers. We love sketches. If you're a mathematician, you love equations and you hate sketches. You want the theoretical solution. If you're an engineer, you love pictures and you'll do the math because you have to do the math. You don't love the math maybe, but you do it because you have to do it. Do your toolbox. So, most engineers think more clearly if they have a picture. On exam, I guarantee you that if you try and sketch something on exam, whether it's a free body diagram, which is essential, ME 214, what it does to you is it builds a time delay in your brain. You don't start writing down and putting numbers in something. And you read the problem, when you sketch it, your mind is working in the background, believe it or not, and it makes life a lot easier if you do it that way, I guarantee it, because the way you get flustered and frustrated is try and start putting numbers on that handheld calculator right away. Oh, that just destroys you. You know, if you're unsure of yourself, that puts you down, way down there. What you do is you build about a 60-second time delay in there, so your mind starts to think about that problem. And one of the best ways to do it is to draw a picture. When you draw that picture, your mind starts to think. It's amazing. The engineering thought process. So anyway, if it's appropriate, not do it all the time, but if it's appropriate, draw a sketch. Once you draw the sketch, I don't care if the problem has it listed there in paragraph form. If you put these guys down and look at the picture, you start to see things. When you write the equation down, you start to see things. What do I know? What don't I know? I know it, I know it, I know it, I know it, I don't know it. Your mind starts to think like that. So much of engineering is have an approach to solve a problem. We're not backyard, in your garage making something. We're not doing that in your garage. We engineers are trained to think correctly. It's pretty fascinating. Pretty fascinating. Okay, so next thing you do, put the equation down in symbolic terms. I don't want to see any numbers in there until you write the equation down so I know you're using the right equation. Then you put the numbers in them. Then you put the units by each number. I'm repeating things. I know I've been beating your head for 3, 4, 5 years, but I'm going to do it one more time. Put the units in. Cancel them out like this. And end up with what you want. All those steps are important steps. And if you do them in the right order, you may be amazed how things kind of fall out. There might be 3 or 4 possible equations. You might write down 3 equations. You look at the equations, you look at what's over here, and you say, no, that's not going to work. 1 equation, 2 unknowns. No, that's not going to work. 1 equation, 3 unknowns. Yeah, he's going to work. So you don't always know. You don't always know which equation might work at the start. Sometimes you do, sometimes you don't. But if you don't, write down the equations you think might work and stare at them. Stare at them a while. Maybe something will jump out at you. Hopefully. Whether it's homework or an exam. And I'll tell you something else. You don't get ready for an exam by copying solutions manual. No. I mean, tell Kershaw, Did you read how to throw the curveball before the game? He said, "Are you kidding me? No, I don't do stuff like that. I throw it myself 50 times on the sidelines. I develop a new pitch, a slider. How? No, I practiced it. I threw it 1,000 times on the sideline." You don't get good until you suffer through some homework and say, "Gosh, I just don't get this." I went through that. I get so mad sometimes. I take my fist and I go, I don't know why I'm not getting this. At home, in my bedroom, nice music on, and touching my hand. But I still got mad. I got so frustrated and flustered. But I worked my way through it, and boy, you're better for it. You're better for the pain. The way you get ready for exams is you're not surprised. And how are you not surprised? You look at all the problems I work in class, you read the example problems in the textbook, and you go over homework. Don't read their solutions because you won't be ready for the exam. Oh, sure, you've seen the solutions, but on an exam, you won't be ready. You've got to practice yourself and put yourself in a tough spot, in a real tough spot. Okay, we have finished chapter 1. Here are your assignments for the next 2 class meetings. So, oh, by the way, my office hours, I can make other times, Monday, Tuesday, and Wednesday. I'm here all 3 days. If those office hours don't match with yours, let me know. We can meet some other time of day. That's fine. All right, we'll see you on Wednesday.